In this video, we're going to take what you've learned about electrophilic conditions with dienes and apply it to a few examples and see if we can really understand these concepts of thermodynamic and kinetic product. We'll go ahead and get started with this example here. It doesn't matter what double bond you start from, but we'll have these electrons abstract the proton. And remember that when you're rewriting the next step, make sure that you put the hydrogen in the correct place to make sure we have this resonance. And I'll have my positive charge here. So now if I go ahead and draw out the resonance structure, the other one, go ahead and go all the way to the other side. I'll have the electrons move here, and then we'll redraw the other resonance structure. And I don't really need to draw that hydrogen again. Have that, that, and the positive charge over here. So in this case, we can have the bromine actually come in and attack one of two places, and we'll start with the structure we have on the right. So we'll have the bromine come in and attack here, which would get us this product. Or I'll go ahead and draw another bromine. We'd have it attack here, which would give us this product. Now what I want to do is label these two respective products as either kinetic or thermodynamic. Now remember that thermodynamic means the most stable product, or kinetic can have a few different meanings, not different meanings, but ways to interpret it based on what proximity effect, like the book in Klein mentions, or the most stable intermediate, which would translate to a lower activation energy when you're going to the next step in the reaction. If we start by trying to identify the thermodynamic product, one thing we can look at is how substituted the double bond is. Here we have a di-substituted alkene, and here we have a alkene that's substituted by 4 different groups. So this would be the most stable product, so we can go ahead and put thermo for this one. Now let's go ahead and continue to analyze what processes would affect the kinetic product here. The book, or the textbook that Klein writes, does say that proximity effect can have an effect on kinetics, which in this case, if we consider that, the fact that the bromine would be close to where the hydrogen was added would allow it to attack more and have a lower activation energy. Another way we can see this is what's the more stable resonance structure in terms of the intermediate? Well, which carbocation is actually more stable? It would be this one, because it's a tertiary carbocation compared to this primary. So this resonance structure over here is more likely to be attacked, so we'd expect that for this left product over here to be the kinetic product. And if we want to add a few more labels to these two molecules, the one on the left would be the 1,2 adjunct, and the one on the right would be the 1,4 adjunct. And the pronunciation is adjunct, not adjunct, as I made a mistake earlier. Before we work through this problem, I do want to mention that it's tempting to create a nice fast rule that the 1,2 adduct is the kinetic product and the 1,4 adduct is the thermodynamic product. But that's not always the case. We always have to define the products based on the way the reaction works out, and you'll see why as we work through this problem. We'll go ahead and start, and we have the electrons in the double bond abstracting the proton. We'll go ahead and write our resulting structure here. I'll refrain from drawing the hydrogen, that is implied. Go ahead and draw the resonance structure here. The double bond move over. That will move our positive charge over as well. The double bond here. That's done. And now we can go ahead and start seeing what our products will look like. And I'll draw a respective bromine for each resonance structure, or each possible product that we could see. Starting with the one on the left, we would see a product that would look like this. Bromine there. And with the product on the right, we would see, or excuse me, the resonance structure on the right, we would see a product that looks like this. The bromine last. This time we'll label the molecules based on where the bromine was added in terms of 1,2, 1,4 adduct, and then that's pretty quick. We know that the one on the left will be 1,2 and the one on the right will be 1,4. But now we want to think about thermodynamic and kinetic products. Let's start by finding the thermodynamic product, which would be the most stable product. And as before, we're looking for the most substituted alkene. So if we look at the 1,4 adduct, which we would perhaps be led to believe would be the thermodynamic product, it's di-substituted as opposed to tri-substituted. So the molecule on the left, the 1,2 adduct, is actually the thermodynamic product. Now let's think about kinetic. If we say that proximity effect is going to play a principal role in defining this product, then our kinetic product would also be the product on the left. But if we consider kinetics in terms of stability of the intermediates, then we have a secondary carbocation on the left and a tertiary carbocation on the right. The tertiary carbocation would be more stable than the secondary carbocation, which means that if that's the principal factor, then the kinetic product would be the 1,4 adduct. Here you should see why that you can't use the 1,2 adduct and 1,4 adduct to decide between kinetic and thermodynamic products. Now don't let this scare you, because in this case we had kinetic could be two different things based on the way the problem's defined, but any problem you have to answer when it comes to kinetic will say that either you're using proximity effect or to not consider it.